Hey everyone, my name is Josh. I am a third year student in materials engineering at the University of McMaster. And today I'm going to be going over a midterm review for the mechanical engineering 3FO4 numerical modeling and solution course. This is going to be a three-part series where I'm going to bring you the first three chapters of this course, excuse me, of this course, and I'm going to be doing my best to go over different aspects of the course, which I thought could have been challenging, and just give you an overall review. Without any further ado, let's get started with part one, which is going to be about computers and error analysis. Just going to title it error analysis. This is a very good introductory chapter. It gives you a lot of background knowledge on how your computer works, and how it can be used to numerically model different problems that can't be solved analytically. Now, we start out the course by talking about significant digits and understanding how we knew what digits were significant. So a significant digit, I'm going to use the term SD, are numbers we can use with confidence in calculations. Now, these numbers are usually numbers that we can see. If we're giving a speedometer and it has little ticks, we can usually see, the tens numbers or the tens numbers and fives. The numbers that we can actually see, along with one estimated digit, are what we can consider to be significant digits. So we can be using the number of certain digits plus one estimated digit. And this estimated digit that is going to be used is the number that we are increasing by divided by 2. And we call this half, the smallest scaled division. So if our speedometer goes up by ones, then our smallest scale division is 0.5. So the estimated digit will be 0.5. If our number goes up by 0.1, then our estimated digit will be 0.05, and so on. Now, hopefully you've learned this in high school, but insignificant digits, leading or trailing zeros are not significant. Meaning numbers like 100,000 or 0.01 only have one significant digit, that being the 1. This is because we can turn each number into scientific notation to make their less significant, or to make the significant digits more accurate. So this would be 1 times 10 to the 5, oops. And this would be 1 times 10 to the negative 2. Okay, hopefully all that makes sense. Now, moving on, we're going to start talking about error. And we were introduced to a couple of different kinds of error. The first one was true error. This was E with subscript T. True error is equal to our true value minus our approximate value. We don't usually use true error a lot in numerical modeling and solutions because if we have a true error, that means there's an analytical way to solve an equation or to solve this question. So why would we use a numerical model if we can solve it by hand? You know what I mean? So there is then this term that comes with every type of error, a percent relative error, or in this case, our true percent relative error. And that's epsilon t, which is just our true error divided by our true value multiplied by 100%. Cool. We then looked at this thing called approximate error. And approximate error is what we use a lot in numerical solutions because it takes into account approximations, which is what we're doing a lot of. This is E subscript A. And this is going to be equal to our newest approximated value, or our newest approximation, minus our last most recent approximation, and there is also an approximate percent relative error, epsilon A, and that's just our approximate error divided by our newest approximation multiplied by 100%. We are then introduced to something called our percent tolerance. This is called epsilon S. Our percent tolerance is our stopping criteria in numerical solutions. So if we were to have to do an iterative method, we would stop when our approximate error is less than our percent tolerance. And this can be found using the Scarborough equation. Where n is equal to the number of significant digits we need. So we now know when our approximate percent relative error is less than our percent tolerance, stop iterating. Perfect. Now we're ready to look at different errors that we find in numerical modeling and solutions. You know what? Before we do that, I'm actually going to go over the difference between accuracy and precision. Accuracy is the measure of how close you are to the true value. And precision, which is a little bit more important in this course, is a measure of how exact our answer is, or how many times we can repeat and regain a certain answer using our solution. So, for example of precision, let's take the number pi. A lot of people say pi is equal to 3.14. But if I were to say pi is equal to 3.14159, this would be a more precise answer because I'm adding more significant digits. The more significant digits that I add, the more precise my answer can be. Now we are ready to go into the different kinds of errors seen in numerical modeling. Now, the first type of error that we're going to be talking about is our round-off error. And just as the name suggests, these error comes from rounding. More specifically, rounding numbers with an infinite amount of digits, like pi or e. Now, before we can truly understand round-off errors, we need to understand how computers take into account numbers, or how computers can display numbers. Now, in the human world, we display numbers using a decimal system, which is base 10. We use the numbers 0 through 9, which are 10 different numbers to display any single number that we can think of. Now, computers use something called the binary base system, which is a base 2 system. They use numbers 0 and 1. Now, the way you read binary is you take the numbers, you're going to multiply it by 2 and raise it to the power of whatever place it's in, starting from the right-hand side being 0, going all the way over to the left-hand side. For example, the binary number 1001 is actually equal to the decimal number 9. The way we do this is we multiply each number by 2 and we raise it to the exponents of whatever place is in from right to left, starting from 0 and going all the way up to how many numbers we have. So this one here is 2 to the power 0 because we're starting on the right-hand side. We're raising it to the beginning number 0. The second one to the 1, the third one to the squared, and the fourth one to the 3. From there, we add all the numbers together. So we will get 2 to the 3 is 8, plus 0, plus 0, 2 to the 0 times 1 is 1. That's equal to 9. After a lot of practice, this is very simple. Now, we're going to get over to a little bit of definitions using decimals and computers. A bit is the smallest part of a computer number. It's the most basic unit of information. This is a 0 or a 1. There's also a byte, which is a group of 8 bits. We also have words. This is a group of any number of bits, but they mostly come at 8, 16, 32, or 64. That being 2 words, or 1 word, 2 words, 4 words, etc. And then the common ones, 8, 16, 32, 64. Nice. Now, not all of the bits in a word are used for the number purpose, right? So that might not make a whole ton of sense, but if I were to say, okay, I'm going to set up an 8-bit word here, I'm going to give us 8 slots. Okay. The first slot here is our sign. All the other slots is our number. The signs go as follows. 0 is positive, 1 is negative. So I were to make my number look like this. What number would this be? Take a second to think about it. Well, I can kind of just forget about these here, just because they're all zeros. They're not going to really factor in for us. But then I know I have a 2 to the 0, a 2 to the 1, and a 2 squared. I can see that I have 0 at the very beginning, so I know my number is positive. 2 to the 0, that's 1, plus 0 plus 4, that's positive 5. Hopefully that makes sense and it's not that bad. To find the maximum and minimum of a certain bit word or a certain number of bits in a or a certain number of bits in a computer system is we're going to take the base that we have, 2. We're going to raise it to the power of n, and we're going to subtract it by 1, where n equals the number of bits minus 1. This is because we have the number of bits that we use for the numbers, and then we have 1 bit for the sign. Now, let's move into a little bit of floating points. These are the most accurate way to represent numbers because they make every single number a decimal, they multiply it by the base, and they raise it to a certain exponent. Floating points are used by taking a certain number m, which is going to be your mantissa, multiplying it by b, which is our base, and raising it to a certain exponent. Most of the time, b is going to be equal to 2, e is our exponent, and m is our mantissa. Your mantissa is always going to be less than 1 because we know it's a decimal. And it is going to be greater than 0, obviously, but in basic floating points or binary, it's going to be greater than 0.5. You'll see that a little bit later. Now I'm going to show you how a computer goes from decimal to binary. It uses a certain algorithm that we're asked to use in this course. To go from decimal to binary, the first step is finding what exponent we're going to have to use. So we know 2 to the x, we know we have a base 2, we're going to raise it to the power of x, has to be greater than a certain number. And this number is what we are converting from binary to decimal. Let's try to find the exponent. What we have to do is we have to take the natural logarithm of each side in order to bring down our x. From here, we divide the right side by ln 2. And now we're going to take the highest, nearest whole number. The highest nearest whole number, meaning if our x has to be greater than or equal to 3.1, we would make our x exponent number equal to 4, right? Because we can't go down, but we also want a whole number. Now, step 2, find our mantissa. The way we do this is, well, we know our mantissa multiplied by 2 to the power of x, which we just found, has to equal our number n. This is very easy. You take your mantissa, you equate it to n divided by 2 to the x. Perfect. We found our mantissa. Step 3, convert it to binary. The way we do this is we're going to make a certain chart. The left-hand side is going to have our decimal. The right-hand side is going to have binary. In the middle, we're going to do this as a reminder. We're always going to multiply our decimal by 2, converting it to binary. We're going to start by plugging in our mantissa in our decimal side. We're going to multiply our mantissa by 2. It's going to give us a number with a leading 0 or a leading 1. Let's pretend it gave us our leading 1. 1 point, blah, 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 blah. What we're going to do is we're going to leave the 1 where it is. We're going to bring the decimal to the right-hand side. Now our decimal is 0 point, whatever was leading the 1. We multiply that by 2. Let's pretend we get 0 point some numbers. We're then going to take that sum number, bring it to the decimal side, 0 point, blah, 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 blah. We're going to multiply that number by 2. Let's say we get 1 point numbers. We bring whatever's behind the decimal to the right-hand side. And we keep doing this. Once we're finished, we're going to have a bunch of zeros and ones on our binary side, along with a bunch of trailing numbers. We are going to then ignore those trailing numbers and only take the zeros and the ones. That is going to be our binary number. We're going to do this until we fill in all of the bits. Now, before we move on, let's talk about different kinds of flowing errors in our floating point systems. The first one is an underflow error. This is if we have a number that is too small for our computer to handle. Our computer cannot access this number. Now let's talk about the opposite, an overflow error. This is if our computer is asked to access a number that is too large for it. There are also two different kinds of rounding. The one rounding we are used to is normal rounding. We're rounding to the highest whole number based off of the 5 criterion. What our computer does a lot of times is it chops. Chopping is when you remove the number directly after the number of significant digits, no matter what it is. So if we had the number 3.141, it would 3.1415. If we were to ask it to chop, it would take the 5, it would just get rid of it, and our number would be 3.141. For rounding, it will round that nearest to the nearest decimal. So when we have 3.1415, we would round to 3.142. We are then briefly introduced to something called machine epsilon, and it defines the bounds of our errors. Machine epsilon looks like this. We are going to equate to our machine epsilon to p, our base, to the power of 1 minus t, where t is the number of bits in the mantissa. This does not include the number of bits in our exponents. Now, the way we're going to define our error bounds if we take the absolute value, actually, we're first going to define chopping and rounding. They've used machine epsilon a little bit differently. Chopping takes the absolute value of delta x, which is the absolute value of our error. It has to be less than or equal to machine epsilon multiplied the absolute value of the actual x that we're speaking of. Rounding takes our error, and we have to make it less than or equal to machine epsilon divided by 2 multiplied by the absolute value of the x that we're talking about. Perfect. That's all we need to know about round-off errors. Let's move on to truncation error. Now, a truncation error might sound simple in theory. When I say, okay, our truncation error comes from cutting off terms, you might think, which is what I thought, that truncation error coincides with round-off errors in terms of chopping. If I were to use my chopping to get rid of some numbers, that means I truncate those numbers, right? Well, actually, no. Truncation error comes from removing values or terms, and we're going to use infinite series. But it can come from removing values or terms in any kind of equation. What we use a lot is Taylor series. Now, a Taylor series is very useful in numerical modeling of solutions, as it takes the value of our function at one point, it takes the value of our function at an alternative point, and from there, we can actually find the derivative of our function, which you'll see a little bit later. We use the Taylor series a lot. Or if we have knowledge of the function's value at point A, we have the knowledge of the function's derivative at point A. If our function and the derivative are both continuous, then we can actually find out where the function is going to be at x plus 1. Let's draw out what the Taylor series looks like. So my function at x I plus 1 is going to be equal to f of xi, our function's value at the current x we're looking at, plus my function's derivative at the current value multiplied by xi plus 1 minus xi. And for simplicity, we're going to keep on calling this from here on out h, our step size. From here, the next value of the Taylor series follows a certain pattern. F double prime of xi multiplied by our step size squared divided by 2 factorial plus f triple prime xi multiplied by our step size cubed divided by 3 factorial. Each of these terms have a name. This is our 0th order Taylor series. This is our 1st order Taylor series. This one here is our 2nd order Taylor series. 3rd order Taylor series, and so on. Our Taylor series is infinite, meaning if we would like to, we can have as many terms. We can have a 100th order Taylor series if we want to. what we learn is as we increased the number of Taylor series terms, our accuracy increases, meaning we get closer to the true value. We also know as we decrease our step size, the weight of higher order terms decreases. This is because we're taking our derivative, we're taking our step size, we're raising it to a large power, and we're dividing that by an even bigger number. That's going to make those numbers mean less because they're smaller. Now, this is where the truncation error comes into play. When we remove terms, this is equal to truncating those terms. When we truncate terms, this takes away terms from our equation. And in part of that, it can also decrease accuracy. Since we know the increased amount of order or the increased amount of terms causes increased amount of accuracy. Taking away those terms decreases the accuracy. The error of our truncation is going to be equal to the remainder of our Taylor series, Ri, which is everything that we've cut off, all remaining truncated terms. Now, if we were to have a first order Taylor series, that means we truncated Taylor series of the order 2 and up. Now, the question arises, how can we reduce truncation errors? Well, we mentioned before, if we have a smaller step size, the smaller the weight of higher order terms. Meaning, if we make our step size smaller, when we truncate higher order terms, we're decreasing the accuracy less and less. So if we decrease h, we can decrease our truncation error. If we take our h that we currently have and we divide it by 2, we directly halve our truncation. If we take our h, our step size, and we divide it by 10, we are making our truncation error a tenth of what it would be had we kept our step size the same. And there's a direct correlation between round-off errors and truncation error, and that's our total error. It's just equal to our round-off error plus our truncation error. And the correlation that it has is between the error and the step size. So we know as we increase the step size, we're also going to increase the error. We also know as we increase the step size, we're going to have a less round-off error because there are less, but we have larger terms, meaning less stuff to round. Now you can see there's a point if we add these two together where we get a certain minimum right here. This means at this minima, there's an optimum step size that we have that minimizes our error. The The final thing I'm going to talk about in this video is error propagation. Error propagation is how errors move through an equation. So for a certain f of x, the error, which we're going to call delta f of x squiggly, which this is the error of the approximation of x. And x squiggly is our approximation. And adding the delta in front of something just means the error. So delta x is the error of x, and so on. The error is going to be equal to the absolute value of the derivative of our approximation multiplied by delta, the error in our approximation, which is just our true x minus our approximated x. And that's all you really need to know. If we want to find what the error in some function is, we're going to equate it to the absolute value of the derivative of the approximation, where we were to grab our function, we're going to input our approximation as the independent variable. Then we are going to multiply that value by our actual true x minus our approximate x. That gives us the error. If we were to have a multivariable function, the same thing goes, except we know we might have a variable x, y, z, blah, 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 blah. To find the error, we're going to take the absolute value of the partial derivative with respect to each variable and multiply it by that variable's error. And so on. All right, that'll finish our video on part 1 on just an introduction to errors in computers. Check in soon for part 2, where we're going to be going over roots of equations. See you later.